learning the XOR problem using our feed-forward network. The XOR function or exclusive OR is an operation on two binary values x1 and x2. When exactly one of these binary values is equal to 1, the XOR function returns 1, otherwise it returns 0. Suppose it is a two-valued function. If we consider two values x1 and x2, what happens is if both x1 and x2 are zeros, the output should be 1. And if output should be 0, and when both values are 1, then also the output should be 0. And when one of the input is 1, the output should be 1. That is the XOR function works. Okay. So these binary values is equal to 1, and the XOR function returns 1. We want our network to perform correctly on the 4 points, that is x is equal to the inputs are 0 0, that is the first one 0 0 0 1, like this 0 1 1 0 and 1 1. So these are the 4 possible inputs to the function. Then the problem with XOR solution is XOR is not linearly separable, so we cannot use any linear model to implement or to represent the XOR function. So suppose we have the inputs x1 and x2. So on the x-axis we have x1 and on the y-axis we have x2. And when x1 equal to 0 and x2 equal to 0, the output should be 0. Okay. Then x1 equal to 0 and x2 equal to 1, the output should be 1. Okay. Then one of the input is 1, the output should be 1. Then x1 equal to 1 and x2 equal to 0, the output is 1. And when both are 1s, the output is 0. So this is not a linearly separable one, because the spreading of the zeros and ones, these are the output values. The values in red color is actually the output values. So we cannot clearly separate these output values with a linear function. That means we cannot draw a line that separates the ones and zeros. Okay, we cannot. If I draw a line like this, on one side of the line there should be only zeros, and on the other side there should be only ones. Then only I can say that it is linearly separable. But in this example, we cannot draw any line that clearly separates the zeros and ones. So hence this is not a linearly separable problem. Then how we can solve this XOR problem? Okay, so one thing is clear, we cannot use any linear model here. Linear models cannot be used to solve the XOR problem, hence we use the activation function at hidden units. So we introduce a new thing called activation function in this. And these activation functions are applied in the hidden units of our network. And these activation functions are actually induce the non-linearity. So we apply a linear transformation on data and then apply the nonlinear activation function. So that will give you a nonlinear function or nonlinear output. And the nonlinear activation function that we use in most of these neural networks are rectified linear functions, rectified linear activation functions. Okay. So how this rectified linear activation function looks like is this. So suppose Z is the input to the linear function, okay, rectified linear function. Then the output will be like this. Okay, the output is represented as g of z is equal to maximum of 0 comma z. Okay, Or in simple words, if I say, if the inputs, this is 0. So here we have the negative values and here we have the positive values. So if the input to the this rectified linear function, or we can call them as a ReLU, okay, ReLU functions, then if the input is negative, that means less than 0, the output is always 0, okay. And if it is a positive value, the output is always a linear value. The output will be linear. Okay. So when we consider this rectified linear activation functions, it has clearly two parts. And these two parts are, when we take them separately, they are linear. This part is linear, and the second half is also linear, but when we take them together, they are not linear. They have a non-linear feature. So it has, since they are partially linear, they have the properties of the linear functions as well. Okay, so it has the properties of the linear models, and at the same time it exhibits the non-linear feature. Okay. So for all the negative values, it gives you the output as 0. And for a positive values, a linear output will be given. Okay. The activation function is the default activation function recommended for use with most feed-forward neural networks. So, ReLU is mostly used in almost all the feed-forward networks. Applying this function to the output of a linear transformation yields a nonlinear transformation. Okay, so finally we'll get a nonlinear transformation out of this activation function. The function remains very close to linear, however, in the sense that is piecewise linear function with the two linear pieces. So we have seen that two linear pieces, one for the positive numbers and the other one for the negative numbers. Because rectified linear units are nearly linear, they preserve many of the properties that make linear models easy to optimize with the gradient-based methods. Okay, so it has the advantages of linear models. They also preserve many of the properties that make linear models generalize well. A common principle throughout computer science is that we can build complicated systems from minimal components. Okay, so the network, the neural network that we use to solve this XOR problem can look like this. Okay, so this is the X1 and X2 are the inputs. Okay, this is the input layer. This is input layer, and this is the hidden layer. And in hidden layer we have two neurons, H1 and H2, and this is the output layer. Y is our output. Okay, it is like that. Then the parameters for this network. Parameters means its weights and biases. Each edge that connects these neurons will have some weight. Okay, so the edge connecting W1 and H1, sorry, X1 and H1, and there are edges connecting X2 and H2. Then similarly, okay, so there are four edges in this between these two layers, and two edges between these hidden layer and the output layer. Okay, so learning. When we train a network, when we train a neural network, what it actually learns is these values. These weights values are actually learned through training. Okay, so these are called the parameters of our network. Then the function, this y is represented like f of x w, capital W, and c small w, and b, which is equal to w transpose maximum of 0 w transpose x plus c plus b. Okay, so this is the function we use here, and we assume that the solution for this XOR problem is like this. Okay, so this is the solution. Actually, these values has to be learned through training, but here we assume that this is the solution. Okay, so the capital W is 1 1 1 1. That means that weight for all these edges are 1. Okay, weight for all these edges as set to 1. Then C is the bias value that we use here. It is 0 minus 1. This also should be learned through training. And small w is 1 minus 2. So this is 1 and minus 2. These are the weights for the um, edges. And B is set as 0. So how we solve this is the inputs. Different input vectors to the network is 0 0 could be one input, 0 1 could be another input, 1 0 could be another input, and 1 1 is another input. So these are the 4 possible inputs to the XOR function with the 2 variables. So x is taken as this vector 0 0 0 1 1 0 and 1 1. Okay, they actually represents the input values. Then multiply it with the weight. Okay, weight is this one. Okay, we multiply it with this w 1 1 1 1. Okay, so when we multiply these two matrices, we will get the value 0 0 1 1 1 1 2 2. So this will be the output of xw. Multiply with the weight. Then add the bias vector c to it. Okay, c is 0 minus 1. So add 0 minus 1 to each rows. 0 minus 1 will give you 0 minus 1. Then add 0 minus 1 to this 1 0, and this will also 1 0, and 0 minus 1. So 2 1. So these are the answers we get. Okay, so when we add the bias vector, we will get it like this. Okay, so it is this is actually xw plus c. Okay, so that is a linear transformation we apply to x. Okay, this is a linear equation. Then we have to apply the non-linearity. That means we have to apply the rectified linear transformation. And what a rectified linear transformation is says that whenever there is a negative value, the output should be 0. Okay, and for positive value, the same positive value will be given as the output. Okay. So for 0 minus 1, 0 will be, we take it as 0. So for 0, the output will be 0 itself. And for minus 1, which is a negative number, the output will be 0. Okay. And this one will be 1 0, 1 0, no issues, to 1. Okay. So other things will be the same. So the output after applying rectified linear transformation is 0 0 1 0 1 0 2 1. Okay, so there is only one change in the first layer because there is a negative number only in the first row only. Okay, now what we have to do is we have to multiply it, multiplying the weight vector. Okay, so w, small w. That means finally we have to multiply it with weight to get the output. Okay, get the output value. We have to multiply it with the weight. Okay, this is small w and this was capital W. Okay, this is the first layer. Okay, this is the last layer between the hidden layer and the output layer. So this is the output after multiplying with W. So what was W? W is 1 minus 2. So we multiply it with 1 minus 2, we will get the output like this: 0, 1, 1, 0. So what it means that When the input is 0, 0, the output is 0. When the output is 0, 1, the output is 1. When the input is 1 and 0, the output is 1. And when input is 1, 1, the output is 0. So that is the interpretation we have. Okay, so that's how we get this output. So first we apply a linear transformation of this function of this input, then we apply a non-linear transformation on it, then we multiply it with the weight values to get the final output. Okay, that's what happened here. Then how we found out a linear, non-linear solution for this XOR problem. So this was our initial original X space with input and outputs. So x1 and x2 are the inputs, and these values in red color are the output expected. And in this space, in this original X space, we are not able to separate it linearly. Okay, and when we transform it into H space, what happens is, instead of x1 and x2, we find this h1 and h2 for in the hidden layers, h1 and h2, and these two values, that means these one values, that is x equal to x1 equal to 0 and x2 is equal to 1, and x1 equal to 1 and x2 equal to 0, these two parameters, these 2 points are merged to a single point in this space, in this H space. Okay, so instead of these two, we converge it into a single point in this learned space, and the other two parameters are like the same 0. So here, now this is a linearly separable problem. That means if I draw a line like this, the zeros can be on one side and one can be on the other side. So it is linearly separable. So that means when we apply some non-linearity to this, or we do some non-linear transformation on this X space, we get an H space that is linearly separable. Okay. So in the left figure, what we see is a linear model applied directly to the original input cannot implement the XOR function. Okay, so the linear model, that means we cannot draw a line that separates the ones and zeros. When x1 equal to 0, the model's output must increase as x2 increases, and when x1 equal to 1, the model's output must decrease as x2 x2 increases. So when you set a linear equation, the intercept should be same, the coefficient should be fixed. A linear model must apply a fixed coefficient W2 to x2. The linear model therefore cannot use a value of x1 to change the coefficient on x2 and cannot solve this problem. So in linear model, we cannot apply this increase and decrease at the same time. So the right hand side shows in the transformed space represented by the features extracted by a neural network, a linear model can now solve the problem. That means after transforming it into H space, we are able to use a linear model to solve the problem. So in our example solution, the 2 points that must have output 1 have been collapsed into a single point in the feature space. That means that that 1 0 and 0 1, they are collapsed to 1 0. H is equal to 1 0 as we said in the diagram. In the linear model can now describe the function as increasing in h1 and decreasing in h2. Okay, in a real situation, there might be billions of model parameters and billions of training examples. So parameters like this weight and biases. Okay, in large networks, the number of weights and number of biases are very large. So one cannot simply guess the solution as we did here. Here we guess the solution like W is equal to 1, 1 and like that. Okay, so these kind of guessing is not possible in real networks. Instead, a gradient-based optimization algorithm can find parameters that produce very little error. The solution we described to the XOR problem is at a global minimum of the loss function, so gradient descent could converge to this point. So there are other equivalent solution to the XOR problem at a gradient descent could also find. The convergence problem of gradient descent, we will see that gradient descent learning in the next session. The convergence point of gradient descent depends on the initial values of the parameters. In practice, gradient descent would usually not find clean, easily understood integer valued solution like the one we presented here. So here we presented a solution like 1, 1, 1, 1, all integer values, all the solution looks neat and clean. But when we go for the gradient descent method, this instead of this one we may get 0, 9, 9, 9, 9, something like that. Okay, so it's not as clean as this result. But our main aim is to find a parameter that approximates our original function, and the error should be minimum in that. Okay, so that is all about the XOR problem. So thank you for